Hello, since I'm not in person today, I'm leaving this video for you. So what I want to look at today is simple harmonic motion. The solutions we've already determined will work, and phasors, which is something totally new. And this is not out of Star Wars. This is right out of physics and math. So let me begin our discussion. Okay, so we had these two different solutions that we've been working with for simple harmonic motion. And remember from last week, adding a phase angle, that's what the phi value is, lets us start anywhere in the cycle of the motion. The first solution on the left would require, without the phase angle, would require us to start at amplitude heading in the negative direction. And then I said that the solution on the right would also be a solution, and they look very different from one another. So by the end of the video, we want to see that they are actually complementary solutions. One solution can lead to the other. They actually will match and give you the same graph. So that's what we would like to accomplish in this video. So actually, starting with the right-hand equation, we had determined last week that if x was c1 cosine omega t, then the velocity has to be omega c1 with a negative, because when we take the derivative of this, we'll get a negative sign, and we chain rule it, and then we'll have an omega c2 cosine omega t. All right, and then we did some substituting. We said at t equals 0, do this in blue, at t equals 0, we can say that x0, x naught, is equal to c1 times cosine of 0 plus c2 times the sine of 0. And sine of 0 is 0, so that goes away, and cosine of 0 is 1. So we determined that c1 must be x naught. All right. Likewise, we, at time 0, the velocity is 0, so we could say negative omega c1 sine of 0 plus omega c2 cosine of 0. This time the sine of 0 goes to 0, so that goes away, and cosine of 0 is 1, so we determine that c2 must be v naught over omega. All right, so that gave us our expression that x was equal to, we could put in x naught cosine omega t plus v naught over omega sine omega t. Now, if it was vertical, we added on an equilibrium height for y, but if it's horizontal, we would leave it at that. So this gives us the equation for the stretch of the spring. Okay, continuing onward, if we go back to the Guy-and-Colley solution, we didn't do the same thing with that where we took its derivative and evaluated it at time 0. So let's go ahead and do that. So if I take the derivative of this, I end up with negative omega a sine omega t plus v. Actually, we did do that. All right. But let's see what happens at t equals 0. Okay, so if we put in at t equals 0, let's actually work with, I'm going to put the velocity in first, okay, and we'll see why. Okay, so I can say that v naught is equal to negative omega a, where a is the amplitude, times the sine. If I put a 0 in for t, the omega t goes away, and we're just left with the sine of v. Actually, don't need parentheses there. Let me just unclutter it a little bit. All right. And if we do the same thing for x, we can say that x naught is equal to a cosine phi. Now, there's a reason that I did the x second, okay? And the reason is that we have a very nice division here. If we divide the two equations, we can say that v naught over x naught is equal to negative omega tangent of phi. Okay, so that would mean that the tangent of phi can be determined from the parameters well, let's finish this. So this would be a negative V naught over omega X naught, okay? And remember that we could figure out omega if we knew K and M. Omega equals the square root of K over M. So if I'd been given K, M, X naught, and V naught, I could figure out the angle, right? Unfortunately, though, I can't use that to figure out what A is, although I can get around that. I can use a Pythagorean relationship, okay? I could, starting with what I have up at the top, I could rewrite the X equation, let's call that equation 1, as cosine omega t plus phi is equal to X over A. Likewise, I could write that sine of omega t plus phi is equal to V. Okay. Oh, actually, I am sorry. Let's go back one step. Let's go back actually to what I have here, 1 and 2. Okay. So I can just have cosine of phi and sine of phi. Let's get rid of that. Okay. So cosine of phi would be equal to X naught over A. All right. And sine of phi would equal, let's see what that would come out to be. That would be V naught over negative omega A. All right. Now, hopefully you remember that sine squared of an angle plus cosine squared of an angle is equal to 1. So we could rewrite this as sine squared was V naught over omega A. We'll square that. You can leave out the negative because we're going to square it. That has to equal 1. So V naught squared over omega squared A squared plus X naught squared over omega squared A squared is equal to 1. All right. We could continue with this if we, I'm sorry, there's no omega squared. I have to put an omega squared up here. Okay. To get a common denominator, I'll make that omega squared X naught squared in the numerator. Okay. Now we can multiply both sides through by omega squared A squared and get V naught squared plus omega squared X naught squared is equal to omega squared A squared. Now, if I divide both sides by omega squared, okay, I end up with this. And if we look closely at what we had before over here for C1 and C2, X naught was C1, and V naught over omega is C2. All right, so I could say that A is equal to the square root of X naught squared plus V naught squared over omega squared. But that is the same thing as saying A is the square root of C1 squared plus C2 squared, which relates it to what we had on the other side. Okay, so I can relate the amplitude back to the constants C1 and C2. Okay, or I could relate the amplitude directly to X naught, V naught, and omega, where omega would be found using the square root of K over M. Now, let me come up with another relationship for this, or that shows this relationship in another way using phasors. Okay. So some of you all of you should be familiar with the idea of real and imaginary numbers. But we can draw something called the real and imaginary plane. This is where the phasors come in. All right. And we're going to consider the solution that we have up above here, that X equals X naught plus cosine omega t plus V naught sine omega t, where the x naught was C1, okay, and the V naught over omega is C2, right? What I'm going to propose is we can represent the cosine function as a phasor. Just draw it in here, which is C1 in length, okay? Now I'm drawing it right on the real axis, and here's why, because C1 is coupled with the cosine of theta. And if you look at a cosine function, let's look at it over time. It starts at its maximum and does this, okay? So what we can do, instead of pretending we have a cosine function, we can pretend that we have this phasor that rotates around in space. And what happens is it's completely real when it's at the 0 position, okay? When it's at the pi over 2 position, okay, if we rotated it over to there, C1 would go away. Well, that's exactly what the cosine function does at pi over 2. And by the time we get over to pi, C1 would be on, this is the positive real axis to the right. It would be pointing in the negative real direction, which would correspond to that point down there, okay? At 3 pi over 2, it would go away again. It would be completely imaginary. And then by the time we get to 2 pi, it's completely real again, okay? Now, where should we draw C2? Well, that's a sine function, okay? So this was y. So if we looked at this, this would look like y equals cosine of x. Now we want to look at, well, C2 is related to the sine function. So let me draw that down here like this. Okay, so the sine function, the reason I drew it down there is because if we're going to rotate, we're going to assume that all rotations are going in the counterclockwise direction. So if we're going to rotate counterclockwise, what would happen is C2 would start out completely imaginary, so we wouldn't see it, but it's rotating to be positive and real if we rotate counterclockwise. Then it will become imaginary again, and then it will become negative and real, and then it will go back to being completely imaginary. So in this graph of the sine function, if that would represent the real part, the phasor that's pointing straight down could just be thought to rotate in the real imaginary plane, and it would in fact be the same as having a sine function. Okay? So that's why we show it pointing downward. Now, what happens if we add our phasors just like we add vectors? Well, it should add up to be that phasor right there, okay? Now, what's the length of that? Well, it would be C1 squared plus C2 squared, which is exactly what we said A squared should be, okay? So it would be the square root, I'm sorry, of C1 squared plus C2 squared using a Pythagorean theorem. So this could represent the amplitude, okay? If we're starting somewhere in the cycle other than at amplitude, we would be off at some angle in this real imaginary plane. Okay, so in this picture right now, we wouldn't be quite at the full amplitude at the starting point, but we would be rotating towards the full amplitude. By the time A rotates over to the x-axis, it would be completely real and it would be its full value. And then it will disappear and it will come back again. Okay, so that vector A is the square root of C1 squared plus C2 squared. I should say that phasor A, that's its magnitude. Now, what is its direction in the real imaginary plane? Well, in the real imaginary plane, it lags behind by some angle that I'll call alpha. Well, if we look at alpha and the trigonometry here, we could say what the tangent of alpha is, okay? Opposite to alpha would be the side C2. We could just as easily, C2 would also be over there and C1 would be down there. So C2 is opposite to alpha. So we could say tangent of alpha is C2 over C1, okay? So we could figure out what alpha is. Okay. Alpha is the inverse tangent of this, but let's first substitute back in. Tangent of alpha C2 was V naught divided by omega, and C1 was X naught. Okay. If I keep going with that, I can see that the tangent of alpha is, if I write it as just a simple fraction instead of a complex fraction, it would be given by that. Well, where have we seen that before? That's the opposite of the tangent of phi, right? Which makes sense. This is the negative of what we get for the tangent of phi. All right. So what does this mean? This means that alpha, the angle alpha in this, is exactly the opposite of the angle phi that would be in the other equation. Okay. So we could say that alpha is the inverse tangent of V naught over omega X naught. We could find alpha, and then phi would just be the opposite of that in order to get the two equations to correspond to one another. Okay, so just continuing onward here, we do have to be careful. This works very nicely if we're in quadrant 1 or 4, okay, which would mean that this whole thing would have to be, we'll be in quadrant 1 or 4 when C2 is positive, okay, or in other words, when X naught is positive. This is true when X naught is greater than, we could say greater than or equal to 0, okay. If X naught is negative, that puts us in quadrant, with our Phasor diagram, that puts us in quadrants 2 or 3, then we would have to say alpha is the inverse tangent of V naught over omega X naught. And remember this, since this has to do with cycles, okay, we want to make sure that we do this in radians. So we add on pi radians, okay, if we are, if X naught is negative. Let me add that, when X naught is less than 0. Okay, so those would be the corresponding things. And then once we find alpha, we can say that phi is just the negative of alpha, right? Now, let's summarize all that we just did, okay? What we're trying to do is show that these two equations, or maybe better yet, this equation and this equation, let me actually relate those, are in fact the same thing, okay? So it turns out they are the same thing if we figure out A, we can say, we can determine A in terms of X naught and V naught and omega with this relationship right here. All right. And we can figure out phi, the phase angle from V naught and omega. All right, we saw that right here by saying, the tangent of phi is equal to this. And we just need to be a little bit careful if the phase angle exceeds plus or minus pi over 2. We may have to worry about what quadrant we're in with that. So you could solve for alpha from V naught and omega naught. This is true, and then you can adjust it based on the quadrant, and then turn around and let phi equal the negative of alpha. Okay, so let me just write down a couple of those equations in summary. If we're given, as in MATLAB, m, k, this really means we're given omega. And then we're also given V naught and X naught. Okay. If we're working with the equation x is equal to C1 cosine omega t plus C2 sine omega t. It's pretty easy to figure out what C1 is just x naught, and C2 is simply V naught over omega. But if we're given the equation x is equal to a cosine omega t plus phi, right? We can find a by saying it's the square root of C1 squared plus C2 squared. We saw that work out a couple of ways, but we could say that's the square root of x naught squared plus V naught over omega, the quantity squared. Okay, so we could find a from that. And we can say that the tangent of phi is equal to, let me just make sure I get this correct, negative V naught over omega x naught. And then just be careful. If x naught is less than 0, add pi to your answer that you get for phi. Okay, and that will make it work out nicely. Okay, so we can figure out what all the constants are in our equations if we have been given if we've been given the mass, the spring constant, V naught, and X naught. And you'll have a few of those problems to do after you finish watching this video.